today we'll look at this topic, industrial gas turbine, which is our last topic, as I said earlier on. Yes, so industrial gas turbines are defined as gas turbines other than aircraft gas turbines, and these are basically turbo shaft engine, and are used in a variety of applications, such as in the oil industry, in the marine, as land transport. And the difference between industrial gas turbine and aero engine or aircraft engine is that these have no limitation on their size and weight. Remember that in aircraft business, weight is something that you would want to minimize. So anything that is heavier will have a weight penalty attached to it. So with this, you don't have to worry about weight and size. Okay? And the good part about these gas turbines is you can use a variety of fuels: natural gas, diesel, even biomass. So now let's look at the advantages of industrial gas turbines. One is compactness, meaning that you can make them to have a smaller mass and volume for a given power output. And they've got low vibration, they're reliable, they're low cost, low emission. Then it's easy to transport them by air, land, or sea. Then on-site maintenance is performed with inspection interval between 25 to 30,000 hours. Then advantages in special application, and these units can be used in electricity generation, and they may be installed on trailers as a mobile source for generating power. An example of this is in 2015, when Zambia experienced a power deficit. They hired a ship from Turkey, and it anchored on a port in Maputo, Mozambique, and it was generating power from there. Then they were tapping electricity using the Mozambique transmission line through to Zambia. So this is an advantage, like they can be transported easily, and the engine can also be used in naval application. Okay, so these are advantages in special applications. However, these sometimes have a disadvantage, and one of their biggest setback is they've got a lot more efficiency compared with a diesel engine. Then they have poor dynamic performance, hence they can't be used like in cars or in application where you need to start and stop. So once they start, they have to continue running for a relatively longer period of time. All right, let's look at the categories of industrial gas turbine. As I earlier said, we've got, so these can be classified as pertaining to land, sea, and air. And in the next slide, there is like an illustration of the different classification. So the first classification, you can have heavy-duty gas turbine. So these are for power generation, ranging from 3 to almost 500 megawatts, with the efficiencies ranging from 30 to 46. Then you've got aircraft derivative gas turbine, and you've got industrial gas turbine. So if you look at this sketch on classification, so you've got industrial gas turbine, application, land, air, and sea. So for land application, you've got power generation, then you've got petroleum field, and you've got vehicles, and under each you've got the type of cycles. Then for air application, you've got helicopters, and for sea, you've got ships, submarines, petroleum platforms, those who are in the oil business. Like if you've got an oil field in the sea, how do you extract that oil? You need an industrial gas turbine. Okay, and the other classification is small gas turbines. So these range in the power output from 0.5 to 2.5 megawatts, and they have a centrifugal compressor and a radio infra turbine, and have relatively low efficiency of in the range 15 to 25. Okay, and we've got micro turbines. Now let's look at the type of industrial gas turbine. So we've got a single shaft engine, and here is a sketch of a single shaft engine. So A, the top figure A, you've got L stands for the load, C the compressor, and two CCs, this double C is combustion chamber, and T is the turbine. So, and this is a single spool with load coupled to a cord. So the compressor is the cord side. So in A, the load is coupled to the cord, or is coupled to the compressor, and in figure B, the load is coupled to the turbine. That's why it's called a hot side. So do not get confused about the nomenclature. And you've got a two spool or a multiple shaft engine, where you've got two sets of compressors and two sets of turbine. And the low pressure turbine, which is T2, is the one that drives the load in this case. Then C is the combustion chamber. So here you can, like in A, you've got two sets of compressors and two sets of turbine. However, turbine 1 drives compressor 2, and turbine 2 drives both compressor 1 and the load. Then in the second scenario, you've got a case where turbine 1 drives compressor 1, and the load is coupled to turbine 2, which is a low pressure turbine, or sometimes it's referred to as a free power turbine. All right, and this is a 3-spool industrial gas turbine. So again, in figure A, you've got turbine 3 that drives compressor 1 and the load, then turbine 2 drives the load, drive compressor 2, and turbine 1 drives compressor 3. Then in figure B, you've got the free power turbine that drives the load, and the turbine 2 drives compressor 1, and turbine 1 drives compressor 2. All right. Now let's look at a single compressor and turbine in an ideal case cycle. An ideal where there are no losses. So in the next slide, we've got the temperature, entropy, and pressure specific volume diagram of an ideal Brighton cycle. And in here, I listed the definition of letters. So C refers to the compressor, I've already explained this. B refers to the burner or combustion chamber, and T is the turbine. So a simple Brighton cycle is denoted CBT, so this means there's only one compressor and one turbine, then in between the compressor and the turbine there's the combustion chamber. And this is a sketch of what I just explained, and you have the TS, temperature entropy diagram, and the temperature and pressure specific volume diagram. Okay. Now, for an ideal cycle, if we make a cycle analysis, we can assume the following. All processes are steady. The compression and expansion process are isentropic. There is no pressure drop in the combustion chamber. And the constant properties, that is the specific heat and specific heat ratios. And the working fluid is assumed to be atmospheric air, and the amount of fuel added is neglected in the energy balance. So this assumption will help simplify the analysis. Okay, so the first component to discuss is at the inlet. And in here at the inlet, the engine sucks air from the nearby area and delivers it to the compressor. And here you assume there are no changes in total temperature and pressure from the ambient condition. That is, the total temperature at entry to the compressor is equal to the ambient temperature, and the total temperature at entry to the compressor is also atmospheric pressure. Then in the compressor, which can either be an axial or centrifugal, and you will learn more about these kind of compressors in the fifth year course. The air and pressure are raised in an isentropic compression, so that the ratio of temperature T2 exit to the compressor divided by entry to the compressor is related to the pressure, and the pressure is raised to this ratio. This ratio of ratio of specific heat minus 1 minus the ratio of specific heat. And P02 over P01 is the compressor pressure ratio, and this equation, I'm sure by now, shouldn't be a problem. And the specific work consumed in the compressor is equal to the specific heat multiplied by the temperature rise between entry and exit the compressor. So if you multiply the temperature rise by the specific heat, then you get the specific work done to drive the compressor. And this same equation here, where the brackets, if you divide through by TA, you can get this equation, and you substitute it by the pressure ratio, and it's the same equation but written in a slightly different way. So sometimes you might not be given the temperature, but you could be given the atmospheric temperature and the pressure ratio, and you could be asked to calculate the specific work done in the compressor. So you should use this equation. And in the combustion chamber, for an ideal case, we've assumed that there will be no pressure drop, and the heat added per unit air mass flow will be equal to total enthalpy at exit, at entry to the combustion chamber minus, 3 is exit to the combustion chamber but entry to the turbine, and 2 is exit to the compressor but entry to the combustion chamber. So the difference, or the enthalpy rise, is equal to the heat added. Right? And finally 4, which is 3, which is exit to the combustion chamber but entry to the turbine. So in the turbine, the product of combustion, which results in a high temperature of the gases, will enter the turbine, and this will expand in an isentropic process to the atmospheric pressure, thus producing power. And this is the same power that is used to drive the compressor. In the expansion process in the turbine, if we assume ideal situation, the pressure at 2 will be equal to the pressure at 3, since we've assumed that there is no pressure drop in the combustion chamber. So the pressure at exit to the compressor and entry to the turbine will be the same. And since we've assumed that the product of combustion after it expands in the turbine will be exhausted to atmospheric pressure, it means that the exhaust pressure will be equal to the ambient pressure, which is P01. And from here we can also, because we've assumed an isentropic relation, the ratio of T03 over T04. So T03 is turbine inlet temperature divided by the turbine exit temperature, and you divide by their ratios. Using this relation, you get the same relation and the specific work generated in the turbine. So the power extracted in the turbine is equal to the specific heat multiplied by the temperature rise. So T3, which is the turbine temperature, minus T04, and this is equal to, if you divide through by T03, you get this equation, and the net specific work of the cycle that is delivered to the load for ideal case, net work will be the work generated in the turbine minus the work needed to drive the compressor. So that difference will be equal to the net work. Okay? And now we look at the thermal efficiency. So the thermal efficiency of an ideal Brighton cycle under a cold air standard assumption is equal to the net work divided by the heat input. So the net work from the previous equation, so equation 4 is the net work. If you divide equation 4 by equation 3, because equation 2 which is the heat input, so what you get out divided by what you put in will be equal to your efficiency. So if you do that, you get this expression, which is equation 4 divided by equation 2. Then this will be equal to 1 divided by this. Then the CP's that are the same, you cancel them out, and you rearrange this equation by dividing it by T01, and if you do that, you will realize that what is in the bracket in the numerator and what is in the bracket in the denominator, if you assume isentropic process, they'll be the same, so these can go, and eventually what you remain with is 1 minus T01 over T04, and this is nothing but the pressure compressor pressure ratio, but the inverse of that. Hence, if you do a simple mathematical manipulation, you will get equation 5 as an ideal Brighton cycle efficiency. And from equation 5, you can note that the efficiency is only depending on the compression ratio, the pressure ratio, and the ratio of specific heat for an ideal cycle. But this will not be the case for an actual cycle, because the other parameters that will have an influence on the overall efficiency, as you will learn later on. Right? Then the specific power is the net power per unit mass flow rate, which can be rearranged from equation 4, and this is equation 4, the net power. So if you rearrange equation 4 for net power, you get this equation for a specific power. Rearranging equation 4, so you by dividing by 3 on your extreme left, and you divide by T1 here, then x2 T02 over T01, which is, this will be the ratio of the compressor pressure ratio, and if you substitute that with the x, then you can get the specific power in terms of x. And from here, you can differentiate the specific power with respect to x and set the results equal to 0. And if you do that, you get this expression where dp over dx is equal to cpt3 over x squared minus cp t01, and is equal to 0. So equating these two and making t3 over t1 subject, what you get is x squared, and from here we said x is equal to the compressor pressure ratio raised to the power specific heat minus 1 over specific heat, ratio of specific heat, gamma. So if you square that part, you just get 2 gamma minus 1 over gamma. And from here, if you make the ratio of specific heat subject of the formula, from here, by C, make it subject of the formula, then you take square root of both, and what you get is equation 6b. Simple mathematics, nothing complicated. Okay, so what we looked at was an ideal case. Now let's look at an actual or a real cycle. A real cycle is one where the heat losses and the processes cannot be assumed to be isentropic or adiabatic, because there will be losses, and yeah. So for a real cycle, if we start at the inlet to the engine, so we begin with the compressor. So the pressure at outlet to the compressor will be equal to pressure at inlet multiplied by the pressure ratio at the compressor, which is equation 7. And the temperature at outlet to the compressor is related to the temperature at entry to the compressor by this relation. And there's the compressor efficiency here, because this is an ideal cycle. So please take note. And also take note that I made a slight mistake. So the numerator here, 1 plus, then this is compressor pressure ratio raised to the power gamma C minus 1 over gamma C. So the C, the subscript C stand for the code. Like the compressor, there's no combustion in the compressor, so this is the code part. So this pi C raised to this ratio, then you need to subtract 1. I omitted the 1 here, so it should be raised to gamma C raised to this ratio minus 1 over eta C, the efficiency of the compressor. So please take note. Here I made a typo. And as before, the specific work of the compressor is similar to the previous equation, and Cp with a subscript C, it means this is the specific heat of cold air. The subscript C stands for cold. So the specific heat of cold air. And now, previously, under ideal case, there were no pressure drop in the combustion chamber. However, there's always boundary layer and frictional losses between the air and the lining of the combustion chamber. So in reality, there will be losses in the combustion chamber. And the factor that take that into consideration is this part, delta C, delta P, subscript CC. So the pressure at exit to the combustion chamber, which is entry to the turbine, would be the pressure at 2 minus this drop. So this drop could be maybe 2% or 3% of the entry pressure. And some manufacturers, they prefer to use this notation, fraction pressure loss, which could be 5% to account for the combustor or burner losses. So this loss is given by this formula, and you can substitute it to get equation 9b. Okay, so this is a sketch of a real Brighton cycle with losses. So you can note that in the previous sketch, we assumed that the pressure at 4, which is exit to the turbine, was equal to the ambient pressure, which in this case is not the same, because as you can see from this diagram, here there's 4 and there's some dots, so the 4 is not joining with this thing. If these two were joining, it means, because these are constant pressure lines, it means that pressure at 4 will be equal to the ambient pressure, meaning that the exhaust from the combustion chamber, after it expands in the turbine, will expand to atmospheric pressure. This is not the case for a real cycle, and you have to take this into consideration when you're doing your analysis. Right? And the maximum temperature is limited by the metallurgical limit of the material used to make the turbine. So T3 is the maximum cycle temperature, and this is a design parameter. You need to determine this way in advance so that whatever energy that is released in the combustion chamber does not result in temperatures beyond what the material can withstand. And if you do an energy balance, you can calculate the fuel-air ratio given by this formula. And this formula is similar to all the formulas that we've looked at before, and I'll not waste time explaining it. Then, since the pressure that exits to the turbine does not expand to atmospheric pressure, it could be slightly higher, and the typical pressure ratio, which is P04 exit the turbine over the ambient pressure, is between 1.1 to 1.2. So this is a typical range. And other scholars have made suggestions that the outlet pressure will be very close to the ambient, at least. So the difference between P04 outlet to the turbine minus the ambient could be 0.01 to 0.04 bars. Yeah, this seems to be a very small amount, but it could be considerable. Hence, if you are given the turbine inlet temperature and the exhaust temperature at outlet to the turbine, the outlet pressure to the turbine, it's possible to calculate the exhaust temperature to the turbine using this formula, where eta T is the efficiency of the turbine and T03 is the turbine inlet temperature, and everything else is known to you. So it's possible to calculate temperature 4. Alright, then the specific work is similar to the one that we looked at, and the specific power to the load. So the specific power, this is like the net power. The power that has been generated in the turbine is used to drive the compressor. Then whatever power that remains is the one that is available to drive the load. So the power available to drive the load is given by equation 14. And this is the specific power with units kilojoules per kg or kilowatt second per kg. And if you know the specific power and the fuel air ratio, you can get the specific fuel consumption, which will be the fuel air ratio divided by the specific power, and the unit of specific fuel consumption will be kg per kilowatt second. And the thermal efficiency for an actual case will be the specific power, the power available to drive the load divided by the fuel air ratio multiplied by the lower heating value of the fuel. Or you can take reciprocal, because P divided by F is the reciprocal of the specific fuel consumption. So the thermal efficiency is equal to 1 divided by the specific fuel consumption multiplied by the heating value of the fuel. Okay? For an actual cycle, if we assume that all processes are steady, then the mechanical efficiencies of the compressor, turbine is equal to 1, and there is no pressure drop in the combustion chamber, then the thermal efficiency can be given by this relation, where alpha is T03 divided by T01. So T03 is the turbine inlet temperature divided by engine inlet temperature, and beta is the compressor pressure ratio raised to the power gamma minus 1 over gamma. So if you substitute them, you can get the thermal efficiency. And the specific power can be expressed by equation 18. Now, let's look at regeneration. We'll look at three processes. We'll look at regeneration, reheat, and another process that will follow. So, if the temperature of the exhaust, like in an industrial gas turbine, the temperature of the exhaust usually leaves the turbine at a higher temperature. For an aircraft engine, this is a good thing because the higher the temperature, the higher the exhaust speed, because the temperature is related to the exhaust velocity. So the higher the exhaust temperature, the higher the exhaust speed, and that translates into a higher thrust. But for an industrial gas turbine, because this is a stationary module that is maybe used to generate electricity, so you don't want the exhaust gas to live at a higher temperature because that would be energy wasted. So to avoid that wastage, you can do the following. Like, the higher pressure leaving the compressor can be heated by transferring heat to it from the hot exhaust. So this hot exhaust which is leaving, you can make a bypass duct to heat the temperature that is leaving the compressor in a counterflow heat exchanger. And this counterflow heat exchanger is known as regenerator or a recuperator. And there's a sketch in the next slide where you've got an engine that is incorporating a recuperator. And X is used to denote an engine with a regenerator. So if you've got CXBT, it means that you've got a regenerator between the compressor and the combustion chamber. So CXBT means you've got one compressor and one turbine, but in between the compressor and the turbine there's this regenerator. And this regenerator is used to heat the temperature that is leaving the compressor. So the highest temperature occurring in the regenerator is T04. The temperature of the exhaust gases leaving the turbine and entering the regenerator. So here is what I just said. So instead of exhausting the high temperature exhaust to the atmosphere, which is a waste of energy because that energy is being supplied by the fuel, so you can make a bypass duct so that this exhaust goes back through 4 here to the recuperator. Then this recuperator can be connected to maybe a steam turbine to heat up the steam and drive a generator, something like that. Okay? So here you've got a single spool engine with a regenerator, and the turbine is driving both the compressor and the load. And below it is the temperature entropy diagram. So now let's talk a bit about regeneration. So the extent to which a regenerator approach an ideal regenerator is called the effectiveness. With a symbol, this symbol is a Greek letter. I don't know if it's epsilon or epsilon, I think so. So this is known as the effectiveness of a regenerator. So the effectiveness of the regenerator is equal to the heat input to the regenerator, which is here is referred to actual, heat actual, divided by the heat, the maximum. So in terms of enthalpy, H05, total enthalpy at 5 minus total enthalpy at 2, divided by the total enthalpy at 4 minus the total enthalpy at 2. So this ratio is referred to as the effectiveness of the regenerator. So when the cold air standard assumption are utilized, it reduces to this ratio, because enthalpy is given by Cp, then the difference in temperature. So if you substitute that and you cancel the ratio of specific heat, because in this case you are making an assumption that there are no changes in the ratio of specific heat. So this relation on top will reduce to this relation. And a regenerator with a higher effectiveness saves a greater amount of fuel. Why? Because the extra heat, the heat that you could have exhausted to the atmosphere, you are utilizing the energy from it. Hence, for the same amount of fuel, you are able to generate more electricity if this is used to produce electricity. Okay, so that's what this statement is saying. However, achieving a higher effectiveness requires the use of a larger regenerator of higher price and causes a larger pressure drop. The effectiveness of most regenerators is usually below 85%. So the more effective you want to make it, the more money it will cost you. So in engineering, there's always a balance that you have to strike. It's good to have a higher efficiency, but if higher efficiency comes at a higher price, then you have to weigh which one are you willing to forgo, or which penalty are you willing to sustain. And from here, you can get the pressure, you can get the fuel-air ratio for a gas turbine that incorporates a regenerator. And you can use equation 20, and the efficiency of this gas turbine with a regenerator is given by equation 21. Then, as I earlier alluded to, the advantages of regeneration is reduction in fuel consumption and consequently a reduction in the fuel-to-air ratio. And this leads to an increase in thermal efficiency, which is a good thing. Okay? Now let's look at reheat. So reheat is proposed at some point in the expansion process for a single shaft configuration. So reheat is similar to installing an afterburner in some turbojets or turbofan engine for aircraft that require a higher takeoff thrust. So a reheat assembly is like a second combustion chamber or an afterburner, similar to that. All right? So on the next slide, we've got an engine layout together with its temperature entropy diagram. So reheat is referred to as R. So CBTRT means that you have this gas turbine with one compressor and the two turbines. So you install another combustion chamber. You've got the first combustion chamber, which is the main combustion chamber, and a turbine. Then in between the first turbine and the second turbine, you have a reheat, which is essentially a secondary combustion chamber. And you can do a thermodynamic analysis. So here you have two fuel air ratio. So F1 is the first fuel air ratio in the first combustion chamber or in the main burner, and it's given by equation 22. Nothing strange, everything is exactly as what we've already learned. And this is a sketch where you have an engine with the main combustion chamber or the primary combustion chamber, and you've got the second combustion chamber or a reheat. Okay? And in here, you should note that when you design this kind of an arrangement, you need to make sure that the maximum temperature in either combustion chamber should be the same, because the maximum temperature is a design parameter, like I've always said. You have to know it in advance, because you don't want to design something where you have a situation where the turbine blades begins to deform or melt. That would be a serious disaster, which no engineer would want to have his name tag attached to it. So you need to make sure that the maximum temperature that will be entering the first turbine is the same as the maximum temperature that will be entering the second turbine. That's why on the TS diagram, you can note T03 is equal to T05. From here, you can tell. And this makes sense. So for some of you that just look at these figures without paying attention, there is a lot of information that this sketch convey. You just have to be a bit observant and make some engineering deduction from the sketches. All right, so we look at the analysis with the reheat in place. So the inlet total temperature of the turbine is defined from metallurgical capabilities of the turbine material. I've already explained this. Hence, for optimum operation, we have the ratio, the pressure ratio P03 over P04. So this is the pressure ratio across the first turbine. Should be the same as the pressure ratio across the second turbine, because P05 is entry to the second turbine and P06 is exit the second turbine. So the pressure ratio across each turbine must be the same. And this should be equal to the overall pressure ratio from the first turbine to the last pressure ratio. If you take square root of that, that is the overall pressure ratio. So if you take square root of the overall pressure ratio, and that should be equal to the pressure ratio of each turbine. Hope this makes sense. And the temperature drop in the first high pressure turbine is given by, so this formula is the same as maybe equation 18. And temperature T3, the total temperature at entry to the first turbine, I've already explained this. This will be known in advance. And pressure for exit to the turbine will obviously be known. And from here you can get the exit pressure at the first turbine. And you can also get the specific work of the first turbine. So this is the same. And for the reheat part, or the secondary combustion chamber, you can also calculate the amount of fuel that will be burnt using this formula, which I'll not spend time explaining because this is obviously known to you. And as I've said, T5 will be equal to T3. These are the inlet temperature. And this is also demonstrated in this slide. T03 is equal to T05 from the TS diagram. Right? And the temperature drop with the second turbine is given by equation 28, specific heat, specific wake for the second turbine. And finally, the power, the net power, or the specific power that is available to the load, which will be equal to the total power that the two turbines will generate minus the power that will be used to drive the compressor. Then what remains is what is available to the load, and that is given by this equation. This is given by this equation. And the specific fuel consumption will be equal to the sum of the two fuel air ratio divided by the specific power and the efficiency by this relation. So the advantages of reheat is it increases the power output. However, the disadvantage is it increases the fuel consumption. So this is similar to an afterburner. The afterburner will increase the takeoff thrust, but that comes at a fuel penalty. You need to burn more fuel because you've got a secondary combustion chamber. So this is similar to that used for aircraft engines. All right. So the third part I was talking about was the intercooling. So we've looked at regeneration, reheat. Now let's look at intercooling. So a third module that may be added is the intercooler. So here we've got a single shaft that is composed of two compressors with low pressure and high pressure with an intercooler in between. Then the second compressor is followed by a combustion chamber with a turbine driving the two compressors and the load. And the subscript for intercooler is I. So an engine that is labeled CICBT is an engine that has an intercooler between the two compressors. For reheat, we had two turbines, but for an intercooling system, we have two compressors and one turbine. In the previous case, we only had one compressor and two turbines. All right? And the minimum possible temperature is again the ambient temperature, and the effectiveness of an intercooler can be defined by this ratio, T02 minus T03 divided by T02 minus T01. So this lower temperature means that the high pressure compressor will be compact. In other words, it will be smaller than its normal size in a non-intercooled engine. Another advantage for the intercooled gas turbine is the high pressure compressor power requirement is reduced. Hence, a higher power can be available for driving the load. However, the reduced high pressure compressor delivery temperature leads to substantially more fuel attaining the same maximum temperature of the normal gas turbine engine. Okay, so this is a sketch of an intercooler system where you've got an intercooler between the two compressors and everything else stays the same, and we can calculate the exit pressure, P4. So P4 is exit to the second compressor but entry to the combustion chamber, and is given by this formula, and these formulas are, by now, they shouldn't be hard for you to understand. They're exactly the same as the previous ones. You just look at where that module is situated and the adjacent module to it, then you can make that analysis. And in the combustion chamber, the fuel air ratio is given by that formula. And in the turbine, the exit temperature to the turbine, which is T06, will be given by this relation, and the power available to drive the load will be equal to the power that is generated by the turbine minus the power that is consumed by these two compressors, which is given by this equation 35. All right, so we've just been looking at single spool or single shaft engines. Now let's look at double shaft. So slide 35, the next slide, is an illustration of a double shaft turbine, industrial gas turbine. So if we analyze the different modules, we can begin with the compressor, and the same equations that we've looked at earlier are applicable. And also in the combustion chamber, we can use the same analysis. So to give you a feel of a double spool engine, you have this one. So you've got two compressors, you've got two turbines. So the first turbine drives the compressor, and the second turbine, which is called FT, stands for free turbine. So it's a free power turbine. So this is used to drive the load specifically. Okay. So the high pressure turbine, which drives the compressor, you can do an energy balance. You can do an energy balance. So the power supplied by the turbine multiplied by the mechanical efficiency of the turbine. So MT stands for the mechanical efficiency, is equal to the work, specific work that is consumed by the compressor, and T4 is equal to this expression. Remember, T03 will be the turbine inlet temperature of the first turbine, right? And for the free power turbine, you can get the ratio of T04 over T03, which is given by this relation. And as if you assume that there are no pressure losses in the duct between the compressor turbine and the free power turbine, then the inlet pressure of the free power turbine is also T04. Okay? So from here, you can get the exhaust temperature given by equation 36, and the power, the specific power, will be given by, for the free power turbine, will be given by the temperature difference between entry of the turbine, free power turbine, and exit the free power turbine multiplied by the specific heat and the exhaust mass flow. So 1 plus F, this is the exhaust mass flow. And because this is specific power, it means that we are dividing it by the mass flow. That's why these ratios. And the fuel specific consumption and thermal efficiency are exactly the same as those we've looked at previously. So now let's look at two discrete shafts or spools. So the two shaft assembly here is composed of two compressors, two turbines, and a single combustion chamber. That's denoted by two C's, one B, and two T's. It is similar to a two-spool turbofan engine. So the low pressure spool shown in the next slide is composed of a compressor. So this is two discrete shafts. So look at this sketch, you've got two compressors and two turbines. And in between the second compressor and the second turbine, there's the combustion chamber. And from here, you can tell that the first turbine, the high pressure turbine, is the one that drives the first compressor and the load. And the second, the low pressure turbine will drive the high pressure compressor. And you've got its TS diagram. So this shouldn't be a problem for you to understand the specific work for the low pressure spool, similar to the previous equation. Even for the high pressure spool or compressors on the compressor side, the equations are exactly the same, and the specific work is exactly the same as before, and I'm not going to waste time explaining this again. And in the combustion chamber, there will be some pressure drop, and this is taken care of by this equation. And the fuel air ratio in the combustion chamber will be given by equation 41. And the exit temperature to the second turbine will be given by this equation. So here these efficiencies, MC is the mechanical efficiency, MC2 is the mechanical efficiency of the second compressor, MT2 is the mechanical efficiency of the second turbine. So please do not get confused what this stands for. So MT2, that's the mechanical efficiency of the second turbine. MC2 is the mechanical efficiency of the second compressor. And everything else is pretty the same and it's easy to follow. Then the pressure ratio across the two turbines. So the pressure ratio across the two turbines is given by this formula. So MT2 is the turbine efficiency of the second turbine. I believe everything is okay. Then we go to the low pressure turbine, which is T1 in our case. The outlet pressure, P06, is known to be slightly higher than the ambient pressure. Then the outlet temperature is determined from this equation. So this equation, eta T2 is the turbine efficiency, and I think everything else is the same. Then the specific power consumed in the load. Remember that the specific power will be the power that turbine 1 is the one, turbine 1 drives both compressor 1 and the load. So the specific power that will be available to drive the load will be the total power that this turbine will generate minus the power that is consumed by the first turbine, the first compressor, I mean. That's why in this equation 45, you've not seen anything to do with turbine 2, because turbine 2 is primarily there to drive the second compressor. And the fuel consumption and efficiency is exactly as before. All right. Then sometimes you can have a 3-spool, like 3 shafts and 3 compressors. Then you've got one combustion chamber in between. and that arrangement is denoted C, 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 B, T, 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 like triple C, B, triple T, to imply 3 compressors and 3 turbines. All right. So, and you can also add an intercooler, a reheat, or a regenerator if you wish. Hence, if more than one intercooler is added between the compressor, then for equal inlet temperature of all compressors, the optimum pressure ratio for each compressor that yield a minimum overall compression weight is given by this relation 46, which is the compressor pressure ratio per stage will be equal to the number of, like the square root of the overall pressure ratio, then you take, I don't know if it's 4th root, whatever you call it in mathematics. Alright, so if you've got 3 compressors, like there's an illustration here. So for 3 compressors and the overall pressure ratio is 27, then you take the cube root of that, then that will be equal to 3. Okay. So even for the turbine pressure ratio, you can do the same as for the compressors, and you get equation 47. Nothing strange, I believe. All right. Then from here, you can get the specific power. So to get the specific power in equation 48, you just multiply it by the mass flow and specific heat. Then you remain with the specific power. Yeah. And in here, there's NRH here is the number of reheat stages, and NIC is the number of intercoolers for a 3-spool which has intercoolers and reheat. And note that in both equations 47 and 48, the working fluid is assumed to be air with constant properties, that is gamma and Cp. Alright? And the rate of heat addition is given by this equation, where epsilon R is the effectiveness of a regeneration system, and NRH is the number of reheat stages, and yeah, everything else is already known to you. Okay, now let's look at combined gas turbine. So, though gas turbine cycles have a greater potential for higher thermal efficiencies because of higher average temperatures at which gas is applied, they have a disadvantage, meaning that the gas leaves at a higher temperature, above 500 degrees centigrade. And this energy was supplied by the fuel. So how do you try to extract some of the energy instead of just wasting it? So in order to extract some energy, you can make a modification to a gas turbine, and that modification you can, like some people have suggested power plant where a gas powered cycle topping a vapor powered cycle, which is called a combined gas vapor cycle, or just a combined cycle. So the combined cycle of greatest interest is a gas turbine or a Brighton cycle topping a steam turbine, a Rankine cycle, which has a higher thermal efficiency than either of the two executed individually. So for a gas cycle that is combined to a steam turbine or a Rankine cycle, this could be implemented in several ways. You've got an open cycle, which is linked to a steam cycle through a heat exchange containing an economizer and a boiler. I think this is what they use in some thermal power plants. Like here in Zambia, I think there's that Ndola Energy. They get the waste product from Indeni, those heavy fuels which cannot be which the heavy fuels, they cannot be used for running our automobiles. Then they get them and they burn them. When they burn those fuel, so they're using heavy fuels which are not useful for maybe automobiles or aviation, and they burn them in the combustion chamber in an arrangement similar to what we've been discussing, but they combine them with a Rankine cycle where the heat that they're generating will be used to heat up water to produce steam, and that steam is connected to a steam turbine, and they're using it to generate electricity, and that electricity is sold to ZESCO. So if we assume specific heat for the gases leaving the turbine, then the energy balance gives the following equations, which I'll not go through, they're easy for you to follow. So Ms is the mass flow of the steam, and Mg is the mass flow of the gas. Okay, and this is a sketch of the arrangement I just talked about. So look at, on your extreme left, you've got a compressor, combustion chamber, and a turbine. And this turbine is coupled to a load, and in this case it's a generator which is used to generate electricity. So now if you observe, the exhaust gases from the turbine, they live at temperatures way above 500 degrees. So why should you waste that energy? That's why in here they've coupled the exhaust to the turbine through a heat exchanger. So the exhaust gases, they'll come here, and there's a superheater where that superheater is connected to a boiler, and that boiler, because 500 water boils at 100 degrees, so if you've got exhaust gases which have a temperature in excess of 500 degrees, it means you'll be able to boil water and produce steam of a certain dryness fraction, sufficient and convenient for power generation, because it's not every steam that is used for power generation. You need steam of a higher dryness fraction, closer to 1, because if steam is in form of droplets, then it can just erode the blades of the generator of the turbine. So you need steam which is superheated, meaning it will not condense, and that's what is used to generate electricity. So the 2 points of electricity generation. The first one is where the turbine is generating electricity by itself, and the second one is where the exhaust to the turbine is attached to this Rankine cycle assembly or a steam turbine assembly, and you're also generating electricity. So in this arrangement, nothing goes to waste. whatever you put in, you make sure that you maximize as much as you can. Okay, so this is a steam entropy diagram, temperature against steam entropy diagram. So I'm not going to detail on this. This is purely mechanical engineering, which add the pressure to land. All right, and you can combine the previous equations to get equation 53, and from here you can get the overall efficiency of a combined cycle. So here WGT, this is the work output of the gas turbine itself, then WST is the work output of the steam turbine. Then if you divide that by the work input from the fuel, you get the overall efficiency of the combined gas turbine assembly. So a few notes from what I've just talked of. So this combined assembly increases the efficiency without appreciably increasing the initial cost. Consequently, many new power plants operate on a combined cycle, and many more existing steam or gas turbine plants are being converted to combined cycle power plant. So you can have thermal efficiencies in excess of 40%. Okay, and I'll not on marine application of gas turbine or combined gas turbine. I urge you to read this on your own. There is some good text in the course textbook I prescribed. However, I will consider to have taught it, and I may ask you some questions. All right, so this is where we end this topic. I thank you so much for your time and have a good day.